Now we are going to discuss embeddings. But before we actually talk about what embeddings are, let's start with something very simple. First, we will print the embeddings for a few words and sentences and look at their size. Once you see how embeddings look in code, it becomes much easier to understand the idea behind the embeddings. Let's jump to VS Code. Let's create new file, emb.py, and now let's import the required libraries. So let's first import from .env. Let's import load_.env from Langchain _OpenAI. Let's import OpenAI embeddings. So here, instead of importing an LLM that generates the text, we are importing the OpenAI embeddings class. Normally, we use an LLM, right? We give text as input and get more text as output. But now we are not interested in the text output. We want embeddings, the numerical representation of the text. So here we are importing the embedding class from Langchain _OpenAI. We are importing this class, OpenAI embeddings. So we can use the embedding models. Let's move on. Next, we have to load our environment variables so we can access the API keys. Now let's create an instance of this class, OpenAI embeddings. Let's assign it to one variable, LLM. If you can see here, this is the class, right, that we are using. And this is the default model available for embeddings, right? So we're not required to use this model parameter explicitly. You can use it, right? But currently we are going to use default embedding models from OpenAI. Now let's take input from the user, enter the text, and let's take this input into this variable text. Now let's use our embedding model dot. This time we have to use embed_query, not invoke, because currently we are working with embedding models, not with LLMs, right? Normal LLMs. And here we have to pass text. Let's assign it to one variable, reply. As you can see here, in place of invoke, we have to use embed_query because we want the model to convert text into a vector. Now let's print this reply, and also let's print the size of this reply as well. Let's save this. I have to activate my virtual environment that we are using since long. Then let's execute embed.py. Let's enter happy. And as you can see, embeddings for the word happy. And in OpenAI, vector size is 1536. So these numbers are the embeddings. This is basically the numerical representation of the text, a kind of meaning code. Please remember this, meaning code. The idea behind embeddings is actually very simple. We need a way to convert text into numbers while still keeping the meaning. Once text becomes meaningful numbers like this, we can compare two sentences mathematically and see whether their meanings are similar or different. If two words have similar meaning, their embeddings will be very close, like happy and joyful will be close, while happy and sad will be far apart, right? So the computer learns meaning, not spelling here. These embeddings are generated by embedding models that you can see here, right? And currently we are using this default model from OpenAI. This is embedding model. So these models are trained on a huge amount of text. And during training, they learn patterns. They learn how words are used, which words appear together, what ideas are related, and how sentences express concepts. Because of that training, we will give any new text. The model produces a numerical vector like this that captures the meaning of that text that you can see here. Right? So this is a numerical representation of our text called as meaning code. Just remember this, right? So now let's try embeddings with Ollama. Let's create new file, emb_ollama.py. To save our time, let's select this code. Let's copy this code and let's paste it over here. So now, as you know, Ollama is running locally on our local machine. So we're not required to load our environment variables, right? Also, we have to import from Langchain _Ollama. We have to import Ollama embeddings. Let's copy this and let's change this class name. Let's keep other things as it was, right? But here we have to use this model. Let's open command prompt. First, let's write Ollama. It's working, and Ollama list. So I have already installed these many models on my machine. Let's use this. Llama 3.2, 3 billion model. Let's copy this and let's paste it over here. So please remember, this model is multi-model, meaning it can generate text and embeddings both, right? One for all. So now let's move down. Let's clear this and let's run this code. Again, same. Happy. Let's press enter. Oh, great. You can see embeddings for the word happy. And you can see the length around 3072. It's very large, right? That means this model represents meaning in a higher dimensional space compared to OpenAI that you can see, right? But the idea is exactly the same. The model converts your sentence or word into a long list of numbers that you can see here, called as embeddings. Those numbers represents meaning. So this is called as meaning code. And you can compare these numbers with embeddings from other texts to measure similarity. So now let's move on. Now let's generate embeddings using Google Gemini. Again, let's create one new file, emb_gemini.py. Let's take this code of OpenAI and let's paste it over here. And now we have to load these environment variables so we can use the key. But here from Langchain _Google _GenAI, we have to import Google Generative AI embeddings, this class, right? So now let's copy this class name and let's paste it over here. Done. But here we have to use this model parameter. Let's move to docstring and here you can see. Let's take it from the example. Let's paste it over here. Done. So we are using this embedding model from Google Gemini-embedding-001. That's all. Thanks to Langchain. Just we have to change the class and model. That's all. Right? Let's clear this. Let's execute this code. Again, same. Happy. Great. You can see. And Gemini also generates long embeddings, right? Same size like Olama, right? That you can see. Again, the important part is every embedding represents meaning, not spelling or grammar, right? That's why here we are generating embeddings. So this way we can generate embeddings for our text using OpenAI embedding models, using Olama, and using Google Gemini, right? Now let's move on. Now that we understand what embeddings are, right? Let's look at a very famous example that proves embeddings actually capture meaning and relationships, not just words. So here is the example. King minus man plus woman is equivalent to queen. So the embedding for the word king contains certain concepts. For example, royalty, leadership, and male, right? So if we think of the word man, the important meaning there is mainly male, right? So if we take king minus man in simple language, we are removing the male concept from the idea of a king. What remains is royalty plus leadership, right? Because we have removed man or male concept from the king. Now if we add woman to it, we introduce the concept female. So mathematically, king minus man plus woman is equal to royal plus male, which is representing king, minus male that represents man, plus female that represents woman. So here we can remove positive and negative male. So it becomes royal plus female, right? Which is equivalent to queen. And that is exactly why the result becomes queen. This shows something very important about embeddings. They do not just store surface level vocabulary. They store deep semantic meanings and relationships, right? The model has learned ideas such as male and female, royal versus non-royal, social roles and categories as well that you can see. This is why the calculation works. And the most surprising thing about this is the model was never explicitly told this rule. It learned these relationships naturally from the large scale text during its training. So embedding don't just help the computer to understand similar meaning, they also understand concepts, relationships between meanings. So you can see this example is proof that embeddings represent meaning in a mathematical space. So now let's code this. Let's jump to VS Code and let's check this concept practically. So now let's create new file, king.py. Let's take the code of OpenAI. Let's paste it over here. With this embedding class, we have to import numpy as NP. Also, we have to import from sklearn.matrix.pairwise. We have to import cosine underscore similarity. So here we are loading environment variables, so we can use keys, creating an instance of our embedding class that we have imported here. Let's close this. Now let's remove this all and llm.embed underscore query. Let's generate embedding for this word king and let's convert it into numpy array so we can do math on them. Let's assign it to one variable v underscore king so we can identify this properly, and let's paste it 4 times. Now let's generate embedding for the word man, vector underscore man, again for one v underscore woman, and at the end we will check with queen. So let's generate embedding for queen as well. Right, done. So here you can see we are generating embeddings for 4 words: king, man, woman, and queen. Now let's create our equation: king vector minus man vector plus woman vector. Let's assign it to one variable analogy. You can use any, and analogy dot we have to reshape it, right? 1 comma minus 1, because we are going to use cosine similarity which accepts vectors in 2D shape, but here is 1D, right? So that's why here we are converting into 2D, and let's assign it back to analogy. Done. After this operation, one long vector called as embeddings will be generated, right? Same, we will compare it with queen vector. So also we have to reshape it. So we can use cosine similarity. Let's assign it back to queen. Let's print similarity and cosine underscore similarity that we have already imported analogy with queen. So as you know, cosine similarity is a way to measure how similar two vectors are based on the angle between them. It doesn't look at the size of the vectors, only the direction. If two vectors point in almost the same direction, their cosine similarity is close to 1, very similar. If they point in opposite directions, the value is -1, opposite meanings, right? If they are 90° apart, the value is 0, completely unrelated, right? Let's save this. Let's open the terminal and let's check the cosine similarity score. So let's execute king.py, and you can see similarity score means cosine similarity score is around 88.32. This confirms that embeddings don't just store word meaning, they store relationships and concepts, which is why this analogy works. Hope all of you are clear with this, right? Now you can understand how powerful these embeddings are. Let's move on. Now let's build a very simple similarity finder. The idea is very simple. The user will type 2 sentences. We will generate embeddings for both sentences using an embedding model. Then we will measure how similar the 2 embeddings are using cosine similarity. As you know, the output will be a number between 0 and 1. Close to 1 means very similar meaning. Close to 0 means both sentences are very different. That's all. So let's take this OpenAI model. You can use Olama or Gemini, any, right? And let's first create one new file, similarity.py. Let's paste it over here. Then also we have to import numpy as np. Also we have to import from sklearn.matrix.pairwise. We have to import cosine similarity. Done. In place of this, let's write enter first sentence text 1. Let's copy this. Let's paste it over here. Enter second sentence. Assign it to 2. Let's save our file, and here let's generate embedding for this text 1. First, let's convert it into numpy array so we can perform math. For cosine similarity, we have to reshape it into 2D. Done. Let's copy this, and same for v2, our second sentence that we have stored inside text 2. Now let's write print similarity score cosine similarity. Here we have to pass v1 and v2. Let's save this. I think done, and let's execute this. Let's enter sentence 1. I am working from home today. And another sentence, I am doing my office task remotely. Let's press enter. So it will calculate cosine similarity between these 2 sentences. Great. You can see similarity score means cosine similarity score is around 91%. You can see these 2 sentences. Meaning is identical. words are different, right? If two sentences have similar meaning, embeddings point in a similar directions. So cosine similarity is high. That you can see, right? Same way you can try different sentences. Just I want to show the use cases of embeddings, how we can use that, right? Now let's move on. As you can see, up to now, we are taking one sentence at a time and generating the embeddings for that sentence. But now we are going to take a few sentences and convert all of them into embeddings and store them as a list. To do that, we are going to use embed_documents in place of embed_query, which is designed for converting multiple text to embedding at the same time. So please remember embed_query used when we want to convert one sentence or one piece of text into an embedding, while embed_documents used when we want to convert multiple sentences or multiple text documents into embeddings at the same time. That's the only difference. Both will generate embeddings, but one works on a single input and other works on a list. That's all, right? So let's create new file, doc1.py. I'm going to take code of OpenAI. As I said earlier, you can use Olama or Gemini as well. Let's paste it over here. First, let's remove this and we are going to use these 4 sentences, right? 1, 2, 3, and 4. And we will convert all of them into embeddings in one go. Place of this, we have to use embed_documents. And here we can pass multiple sentences that we have stored inside this list. I think done. Just let's remove this, let's save this, and let's execute our code. Great, you can see total we have 4 vectors, means 4 embeddings, 1 for each sentence. Let's find the length of this. Save this, clear this, and let's run this. You can see output is 4. We have 4 vectors, right? Let's print embeddings for this first sentence. So reply first, and I'm going to print first 5 numbers only, right? Not all. Let's run one more time. You can see we have total 4 vectors, means 4 embeddings. These are the first 5 numbers of the embedding for this sentence. Hope all of you are clear with this, right? So with embed_documents, we can quickly convert multiple sentences into embeddings. After that, we can perform similarity tasks that we have performed earlier, just to compare how close the meaning of 2 sentences is using cosine similarity, right? Hope all of you are clear with embeddings. Let's move on.